Okay, so we're dividing the sum into two parts, one of which doesn't depend on dn and the other of which does. And so we can write the latter as E1 is equal to C1, that's 1/2 sinc 1 over 2, minus D1, which is alpha over 2j e to the j phi magnitude squared. And then the second term, of course, is 1 over 2 sinc 1/2 plus alpha over 2j e to the minus j phi. Okay. And so the idea is we want to, as stated in the problem, we want to choose alpha and phi so that the mean squared error is minimized. This is the mean squared error. Alpha and phi only appear here and here. Okay, and so the idea is to minimize each of these terms. Let's just look at one of them. Let's just look at the first one. We have a real number minus something else, which may or may not be real. However, we are free to choose this phi as we please, so we can actually make the second number real if we like. Okay, and secondly, let's take a step back and look at this. This is the magnitude squared of some number, right? And so if we want to minimize this, we would want to make ideally that number equal to 0. Okay, because it can't be less than 0, right? So if we want to minimize the error, we make these two terms equal to 0. So let's just try that. Let's just try alpha equals 1 and phi equals pi over 2. Okay, so let's look at this term. 1 over 2, and then this e to the j phi and the j in the denominator cancel out. Okay, so actually, excuse me, this should be alpha equals sinc 1/2. Okay, so if alpha equals sinc 1/2, then alpha over 2 is sinc 1/2 sinc n over 2, and then this j cancels with the e to the j phi in the numerator, and you get 0. Right? Similarly, for the second term, we have phi equals pi over 2, so this numerator and denominator, the j minus j and j give you a -1. Then we have alpha over 2, which is sinc 1/2 over 2, so this term is also equal to 0. So if we make this choice, we actually find that so we say if we make this choice, then we find that the error, mean squared error, is equal to the sum for n is not equal to 1, cn squared. So in fact, it is minimized, right? Because the best we could have done was to make these two terms 0, and that's in fact what we did. Okay, so that's the first part. Then the second part is to state what the mean squared error is, and that is, of course, the sum of all the other terms in the Fourier series expansion. And so we can write this as equal to the sum of all the terms, which we actually know how to get. Minus these two terms. Okay, the plus and minus 1 terms. This one here we know is equal to by Parseval's theorem, it's equal to the power, or the average power, in f of t, right? So what is f of t? Well, f of t was this here, right? And if we ask if it's equal to 0.5, right, then the square is equal to 1/4. If it's equal to minus 0.5, then the square is also equal to 1/4, right? So this guy here is equal to the integral from, let's say, 0 to 1, right? It's the integral over a period of f squared of t. And actually there should be an absolute value here, but it's not going to matter. Dt minus c1 squared minus c minus 1 squared. Okay, and so this is equal to 1/4, and this we know is equal to 1/2 sinc 1/2. Okay, so we simplify this further, we get this is equal to 1/4 minus this is 1/4 and 1/4, so we get 1/2 sinc squared of 1/2. Okay. So that's problem 1. I'll note that this particular question, in particular part D, was considered to be quite difficult. Okay, so if you can get that, you're doing very well. Okay, so next problem. You're told that a system defined by an operator L is linear and time shift invariant with the following impulse response, or with a real valued impulse response. So we don't know what that impulse response is. Real valued means we know that there is a certain symmetry. So there's going to be a Hermitian symmetry, which is that h of minus f, right, is equal to the conjugate of h of f. Okay. So these in your mind should go hand in hand. You characterize it by applying sinusoids at varying frequencies greater than 0 and measure the corresponding outputs. Okay, you find that when x of t is given by cosine 2 pi f naught t, so it's a cosine with frequency f naught, that y of t has this form. Okay, so the idea is it comes out as a cosine with another frequency, with the same frequency f naught, right? It has to be the same frequency because it's a linear shift invariant system. And there's a phase shift, right? And so that phase shift is going to give us information about what's going on. And it says the y of t is equal to this if the frequency, right, the input frequency falls in this range. Otherwise, it's equal to 0. right, if the input frequency falls out of this range. Okay, so this is kind of thinking in reverse from how we've done these problems before. So in other cases, you would be given the transfer function and you'd have to find out what happens to a sinusoid. You put in a sinusoid at the input, what happens at the output. In this case, you're told the input and output, right, or the output for a given input, and you're asked to find the transfer function. So the principle is the same, you're just asked to apply it in reverse. Okay, so this is 2a. So draw and sketch the magnitude of the transfer function. Well, we know that y of t, right, so if x of t equals cosine 2 pi f naught t, going into a linear shift invariant system, we know that y of t will be given by, so there are a couple things to remember. So one is we have the amplitude of the sinusoid scaled by the magnitude of the transfer function. The frequency of the sinusoid does not change, so f naught again. And then we also have this phase shift, given by the phase of the transfer function evaluated at the frequency of the sinusoid, right? So this frequency has frequency f naught, and so that defines the amplitude scaling and the phase shift. Okay, so now we know the transfer function. We know the transfer function has this form. We know the input and the output for a range of frequencies, and so the question is, what is the transfer function? Well, if I were to draw this, so I look at what's said in words here, I can actually draw the magnitude and the phase of the transfer function. So let me go ahead and do that. So I'll put the magnitude straighten this out here. Put the magnitude over here. And the phase over here. Okay. Excuse me, the phase has to look like this. Okay. Now we know that as per the problem statement, let's just look at the magnitude, okay? So as per the problem statement, if the frequency is less than 1 over t, then the scaling is equal to 1. Okay, and if it's greater than 1 over t, y of t is equal to 0, right? So it's going to look something like this. And actually, we didn't specify what happens at f naught equal 1 over t, right? So let's just choose it equal to 1/2. Okay. Now, because we know this is for positive frequencies, right? Because we know the function is real, we can actually say what's going to happen for negative frequencies, right? So we know that for negative frequencies, because this holds, h of minus f is a conjugate of h of f, that in particular the magnitude at minus f is equal to the magnitude at a positive frequency. So we can actually extend this out just by reflecting about the f equals 0 axis. We can extend out and say what this would look like. Okay, so that's the magnitude. Now the phase is a little bit more tricky, so let's look at this expression here and this expression here. So of course the frequency doesn't change. Now the phase is going to be equal to the phase of the transfer function, right? So every time I put in a frequency, I can sample the phase of the transfer function. And in particular, this phase goes linearly with the frequency, right? And it's negative, so it's going to look something like this. And it keeps on going until 1 over t. Actually, it's not going to matter what the phase is for f greater than 1 over t because the magnitude is 0 anyway. Okay. But let's just draw it up to 1 over t. So at 1 over t, this number here is equal to 2 pi times 1 over t times 1 over t, so that's just equal to minus 2 pi. Okay, and we go, now the magnitude was symmetric because the function was real, and now if we look back up here, and we actually did this in class, if we look at the phase, right, the phase of h of minus f is equal to minus the phase of h of f, right? So the phase is going to have the opposite odd symmetry, so it's going to be reflected about the origin. Not reflected, but it's going to be anti-symmetric about the origin. Okay, so whereas the magnitude was had mirror symmetry, this has odd symmetry, or it's anti-symmetric. And again, at minus 1 over t, the phase is equal to 2 pi. All right, and some people drew this as 0 for greater than this, but since it's h of f is equal to 0 for f greater than 1 over t, we can define this phase however we like. So let's just define it as being a linear phase, right? Okay, so if we draw the equation for this, you can convince yourself that this is equal to minus 2 pi t f. Okay. So next question is okay, well, actually we have to finish this question. It said sketch the magnitude of the phase. Okay, so we can actually, it's not explicitly asked for, but we can write that h of f is equal to rect t f over 2, right? Because this rect function extends from minus 1 over t to 1 over t. if you work this out, that would require a scaling of 2 over t in the denominator. Okay, that's the magnitude, and then we have the magnitude times e to the j times the phase, right? And the phase is equal to minus 2 pi t f, right? Okay, so part B says when the input is a delta function, what is the output? Well, we know that the output is given by the impulse response, which is the inverse Fourier transform of the transfer function. And so let's assume t is greater than 0, because I don't want to carry around magnitudes. Okay, so h of t is inverse Fourier transform of this. And if we work that out, this is actually the combination of two properties. You have a complex exponential here, which is going to shift, right? And then you also have scaling. Okay, so let's just think in our minds what is going to happen. So rect of tf over 2 inverse Fourier transforms to 2 over t sinc 2 over t times t, little t, right? And then if we include this here, this complex exponential, it's going to shift in time, right? So that's going to shift this response in time. And how much is it going to shift by? Well, if we look at our properties, it's actually going to shift by capital T. Okay, so what we're going to be left with is this response, or this function shifted by capital T. So we're going to get 2 over t sinc 2 over t times little t minus big T. Okay, last question. When the input is a unit step function, find the expression for the output. So this is a convolution problem, but it does say we can leave it in integral form. Okay, so the easiest way to do this is we can obviously flip or shift whichever term in the convolution we'd like. So we have y of t equals s of t equals x convolved with u of t which is equal to now let's flip and shift the u, the unit step function. So that's going to give us u, have to define a dummy variable first. Let's call it tau. So u of the output variable minus the dummy variable, x of the dummy variable, which x is obviously h here. Okay. And so we can simplify this by noting that for the argument of u greater than 0, it's equal to 1, right? So t greater than tau, this is equal to 1, or in other words, tau less than t, u is equal to 1, right? Otherwise, it's equal to 0. So basically, we can change this, take this out of the integral by just integrating from minus infinity to t, right? Because all other values of tau in the integral aren't going to contribute. And then we have here h of tau d tau. Got rid of the unit step function. Okay, and now we can fill in for h of tau. That's going to be 2 over t sinc of 2 over t, that's big T, our dummy variable, minus big T. Excuse me, this has to be